before we have to move on to the more difficult factoring. Now, I want us to do a little warm-up because I want you to see where some of this comes from before we have to factor something that looks super, super complicated. So we're going to walk through this together just to make sure everybody's on the same page of how to tackle a problem like this. We're going to multiply this out. Now, I always get this question. What do I do with the -3? Personally, I save it to the end. Okay, I wait until the end. I multiply those two binomials. I multiply those out first, and then I distribute the -3 to everything. Because technically, you could distribute the -3 to one set of your parentheses, and then you could FOIL it out. But you do not distribute it to both sets of parentheses. So that's why I always just save it to the very end. All right, so let's refresh ourselves on some of our exponent rules here. When we FOIL this out, we've got 2x squared times 2x squared. So 2 times 2 is 4. When we're multiplying with exponents, what do we do with the exponents? Add them. So that's 4x to the 4th. When we multiply the outside two terms, 2 times -3 is -6. We've got x squared and we've got y squared. They don't have the same base. So all we can do is write x squared, y squared. We don't change the exponent at all because they don't have the same base. Then when we multiply the inside, -3 times +2 gives us -6 again. We've got y squared times x squared. I always just like to write it in alphabetical order. Okay, even though the y squared technically came first in the problem, I write it in alphabetical order. Then when we multiply the last, -3 times -3 gives us +9. Y squared times y squared is y to the 4th. Now, before I distribute the -3, it'd be great if I could combine some like terms inside of my parentheses, and I can. We do have two terms that have x squared, y squared, so we can combine their coefficients. So we've still got 4x to the 4th, but now we have -12 x squared, y squared, plus 9y to the 4th. And then finally, we can distribute that -3 to get our final answer. Okay, so I don't know that we were going to get to this specific example later on today, but our goal in factoring, I'm going to show you, this is something called a quadratic form, and it is a perfect square trinomial because we multiply the exact same two factors. I think I mentioned that yesterday, that perfect square trinomial idea. When you multiply the exact same two factors, the result is what we call a perfect square trinomial. The first and last terms are perfect squares, and the middle is 2 times the product of those perfect squares. So we're going to be able to factor what's in red. We're going to be able to take it back to the original step by the end of tomorrow. Okay, but I wanted to show you where it comes from by multiplying it out. Okay, so we're going to go back and we're going to do some more simple examples before we get to something as complicated as what I just showed you. So we're going to review factoring quadratic expressions. And like I said, some of our examples are going to come from that worksheet there. Okay, so first thing that we need to remember is anytime we're asked to factor, we should always look for a GCF. Very first thing. And then after we take out the GCF, we need to see if we can do any further factoring. So let's look at number 2 there on your paper. 3n cubed plus 27n squared plus 42n. We're going to start by looking for that GCF. Do all 3 of my terms have something or more than one something in common? So we always look at the numbers. I heard somebody say yes. You're correct. Okay. I always look to see if that leading coefficient is the GCF, because that makes life a lot easier if it is. And in this case, it is. All 3 of our terms are divisible by 3. So 3 is a part of our GCF. And then all 3 of our terms also have a variable. They all have an n in them. Some of them more than one n, but a minimum of n. So 3n is our GCF. So we're going to factor out that GCF. Now this helps some people to be able to determine what's supposed to go inside of our parentheses. So this is how I think about factoring out a GCF. Technically, I'm going through and I'm dividing all my terms by the GCF. And that's going to tell me what to put in my parentheses. Okay, so 3 divided by 3 is 1. I'm not going to put a coefficient of 1. When we are dividing with exponents, what do? Subtract. Okay, think of that division symbol, that line, as a minus sign. So 3 minus 1 is 2. We're left with n squared there. Okay, positive 27 divided by 3 is 9. N squared over n is just n. And 42 divided by 3 is 14. N divided by n is 1. Again, I'm not going to put 14 times 1. I'm just going to leave it as 14. Okay? Now, we're not finished. N squared plus 9n plus 14 can be factored further. Now, this is a pet peeve of mine. People don't bring down the GCF on their next line of factoring. Just because you're not doing anything with it doesn't mean that it can just disappear. You got to carry it all the way through your problem. Now, this is an easy one to factor because a is 1. That leading coefficient is 1, so I can automatically put n and n. The last sign is a positive, so that means that my signs are the same. My first sign is a positive, so that means they are both positive. And then 7 times 2 is 14. 7 plus 2 is 9. Don't forget what I mentioned the other day. You can always, always, always check your factoring by multiplying it back out. Okay, I'm not going to at this point, but you can always do that. All right, so let's make sure everybody's on the same page with factoring with the GCF. I would like